So, the both end column is hinged, this is called ideal column. The load is applied centroid in the at centroid and axially, and so look at initially the P is the load applied which column did not buckle. So, I go on increasing the load at particular point where the PCR is obtained, then the column starts buckling. Forget about this F load, I mean what you are seeing here, it is not like that. We are not going to apply like this, but it is imaginary. At particular point of time when I apply a load PCR, so column starts buckling, right, column start buckling, that load is called critical load. So, it is a point where columns start buckling, but any point P is less than or equal to PCR, column did not buckle, even at the point of PCR. A value P more than PCR start buckling, is buckled. So, now exactly I cannot say after PCR 1 gram or 2 gram of load, additional gram of load, the column started already buckled. Okay, very important. Up to P less than or equal to PCR, the column did not buckle. Okay. So, beyond that is going to buckle, okay, that we will see. Okay. Now, what we do, do not worry, these are things may be required. Okay. So, now buckling. So, now our idea is how to find out this PCR. Okay. So, we are trying to see how to find out PCR, what is the way out, how to know that at what point they start buckling, so that my value is always less than the PCR. So, apply load, this is a, we can say almost a critical load, that means the load which the capacity the member has, and I want to apply a load is P, the P load is applied. So, always I can be careful. So, let us take a case with this particular example. So, I have a column, right, I have a column with both end hinge, you know how to do that. Okay, fix here. So, do like this, and of course, it is guided by other both ends, and this is supports. Now, I apply a load P and continue applying a load, what happens? You will see that this will start buckling at particular point, let us say some PCR, right. Now, if I try to take a free body diagram of this deformed shape, right, if I take a deformed shape free body diagram, and if I try to see, maybe I just take very little portion, right. So, now if you carefully observe, right, what I am doing here, I am applying a load P, right. Let us say P, PCR is the point where you have to see, PCR will see the point afterward. Let us say point a P, a load applied. So, now what will be load in the member at any point of the member will have a load P, right. Now, and then this has got deformed, let us say amount of E, or let us say at a distance x from one end, distance from x at one end, this displacement I say, let us say V, right, let us say V, or Y also does not matter, let us say Y, let us say the displacement at distance x is, let us say Y, let us say the displacement amount is Y, Now now if you look at carefully this particular member at this point, I am talking about the previous diagram, look at here. So, I am applying load P here, and at this particular point there is a P load, but apart from the P load, because this has got deformed some amount, so it has got a movement also which is M, right, very important. So, now if this looks like for equilibrium portion, for the purpose of equilibrium, what I can write, this is like a bending shape, right, the bent shape. So, the bent shape, the equation of equilibrium. So, what I can do, E I, that you have already seen, E I d square y by d x square equal to M is a equation of a member which is bent and having because of the movement, but it is bent anyway, and I am trying to write the movement here, okay, very important. And this member has got some Young's modulus and it has got momentum inertia. So, now this can be written in the form of this differential equation, this already you have learnt it. So, now what is this moment at this particular point? The moment nothing but this M will be nothing but the load applied P into y is the distance it got a deformed laterally, and the moment being a anti-clockwise a minus value. Okay. This is the differential equation, or when M over E I, that you have said at curvature, fundamental equation of the moment and curvature, right. M over E I you have seen, right, M over I is equal to F by y is equal to E by R. So, I am writing this R is nothing but your curvature. I am taking these first two terms, I mean first and last terms. So, M over I is equal to E by R. So, R nothing but d square y by dx square. So, M equal to E I by R, right. So, R 1 by R is called curvature, right. So, that is what I am using here. So, now what I do, E I d square y by dx square equal to minus P into y, right. So, if I take this to be left hand side minus, so what I get, or I can just take this E I other side, I mean the down. So, d square y by dx square plus P by E I y equal to 0. Now, if you look at carefully, this is an differential equation. This is a differential equation of 2 degree, and you have learned, I think, part of differential equation in the mathematics. You will agree with me that you have learned the differential equation solution. So, the solution of this equation will be, if you look at carefully also the previous diagram which I shown here, you see the kind of bent shape it is there, right, one curve and this is second curve, right. So, this meaning that this particular column bend like a sine function. It is very important to understand this. This particular equation bends like a sine form. So, in general the solution of this equation will be like C1 into sine of root of P by E I x plus C2 into cos of root P by E I. So, remember this root is full E I, x is outside. This is the form, this is a kind of solution we can see. It is like what we see the sign in terms of sine and cos, it is general solution. So, this is a general solution, this is general solution of the differential equation for this differential equation. So, this is a differential equation, differential equation, and solution is this. Now up to the, if I can somehow find out C1 C2 based upon the boundary conditions, my solution is right. So what I do, this substitute the boundary conditions. So what are the boundary conditions, right? So somehow if I can substitute the boundary conditions, then my assumed solution is right, where I can find out C1 C2. So first boundary condition will be, look at the diagram here, this one or this one, at x is equal to 0, what is y value? 0, right? So at x is equal to 0, y is equal to 0, it means there is no displacement at a first point, and this is a boundary condition 1, BC1. The second boundary condition is, at x is equal to L, again displacement is 0, right? There is no deflection at the top and bottom, is it not? So this is your boundary condition 2. So just applying these two, I can get the C1 C2. How many unknowns are there? 2 unknowns. One is C1, second is C2. So how many equations I got? 1 and 2. So definitely I can find C1 C2. So let us say apply the first boundary condition. So y in this equation, assume solution in this equation, apply the x at x is equal to 0. What happens? Y becomes 0. What I said, right? Y is 0 is my boundary condition, equal to C1 sin root whatever is the coefficient here into 0, right? X is equal to 0 plus C2 into cos everything 0. So sin 0 is 0. So the entire thing is gone, right? So I left with a 0 equal to C2 into, so cos 0 is 1. That means C2 is equal to 0. So I got a coefficient C2 is equal to 0. Now let us apply to the second boundary condition, right? So y equal to how much? Second boundary condition, y equal to again 0, equal to C1 sin root P by EI, x is equal to, here what is x here? L, right? And plus C2 into, not required, and anyway I got C2 is equal to 0, so I do not need to use that at all. So this implies C1 sin root P by EI of L equal to 0. So this is a equation I got. Now try to understand. So I cannot find out C1, right? Now because it is like a trivial solution, if you look at carefully, if C1 equal to 0, I mean in this, if this is the equation I got finally, that means either C1 is equal to 0 or sin of root pi by EI into L equal to 0. Either one has to be 0, both cannot be 0, right? Let us see whether C1 is equal to 0 possible or not. Let us see whether C1 is equal to 0 possible or not. Let us see. If C1 equal to 0, go back to your equation. If this is equal to 0 and we already got that C2 is equal to 0, then what is y? Y must be equal to 0. Y must be equal to 0. So if y equal to 0 means at all values of x, the y is 0. That means there is no deflection. That means there is no buckling. Is it not? So it means column is straight throughout the length and no buckling, which is not true, because we are discussing about the buckling of the column. That means C1 cannot be 0, right? So if C1 equal to 0, if C1 equal to 0, column is straight. If column is straight for all values of P, that means there is no buckling. So, which is not true, because at particular value, which is not true, right, because at particular value column has to buckle, that means C1 cannot be 0. If say C1 0, column will be straight, never bends, never buckles, no matter how much load applied, which is not true. That means C1 is not the 0. So, if C1 is not the 0, other factor must be 0. That means the sign other C1 into this, right, 0 means other one, C sine of root P by EI into L equal to 0. This must be 0. If this is 0, then we also learned from the trigonometric functions what is the values of this solution. Sine of some sine of x equal 0, right. If sine x is equal to 0, what is the value, what could be values of x? We know that is n pi, is it not? If sin x is 0, sin x is 0 only at x is equal to n pi, it means n is equal to 1 pi, right, and 2 pi, 3 pi, 4 pi, for all n integer values n is equal to 1, 2, 3, so on, this sin x is equal to 0. Same thing we will try to see. That means the solution of
n equal to 0,
n equal to 0 undadu. N equal to 0 means there is no loop, we cannot see, that is not real, imaginary, that n equal to 0 we cannot see at all. Okay. Start from n equal to 1. So, that is possible loop. That means column, if I look at a column here, this is one loop, n means one of the mode, n is, although it is and mathematically is integer, for structurally for civil persons it is a one loop. So, this is we can see that n is equal to 1 loop. We cannot say n is equal to 0, nothing can be seen. N is equal to 2 means it is something like this, n is equal to another 1, right, n is equal to 2 loops, we call it as the mode 1, mode 2. So, mode starts from 1, mode 0 undadu, means physically n 0 not possible, physically, mathematically n can start from negative value, n can 0, but physically n here not possible, imaginary not possible. So, physically n is equal to 1 start, that means root P E I into L must be equal to n pi, right. So, let us discuss about n is equal to only 1. Now, let us start with, forget about it, n equal to 0. Let us first take that value. So, what if squaring both sides, what happens? Squaring both sides, when is right, what happens if square both sides? P square, sorry,
P by EI into L square equal to n square pi.
P by EI L square is equal to n square pi square. Okay. This implies P equal to n square pi square by L square into EI, right, very important. Now, the n is a mode number, loop number. So, I will tell you what is the significance of this n, this is particular mode means. So, it means if n is equal to 1, P equal to pi square EI by L square, that means if n is equal to 1 is P 1. So, P 2, the P 2 equal to n is equal to 2, right. For n is equal to 2, what happens? 4, right, 2 2 is 4. So, 4 pi square EI by L square, try to understand, pi square 4 pi square EI by L square. Now, for the same, I am not changing anything, right, simply the same thing, when n is equal to 1, the load is P 1, at load is equal n is equal to 2, load is P 2. That means, how many times of this? What is P 2 by P 1? P 2 by P 1 is 4. That means, if you want to get the 2 loops in the column, 2 modes in the column, you have to increase the load 4 times. Please understand, these are very important practical questions. In order to get the second mode in the column, you need to apply 4 times the load. So, I already demonstrated, I think, during your applied mechanics. So, I have now I have a scale in my hand, which you cannot see. After the video you will see, when I send that recorded one. So, the scale you can try to bend it, right. So, you will see one loop, right. Now, you can ask your friend to hold in the middle, then you try to apply a load. You have to apply more load, more means 4 times load. Then do not ask your friend to move it, but let it be there holding. Then you continue applying load, then you will see 2 loops. You will see the 2 loops which you see here. This what you are seeing here, this one. So, this particular phenomena you will see only 2 loops, only when you see the P equal to 4 times PCR, 4 times, right. So, that is what you can observe, 2 loops. And then if observe somebody, what I am saying, you ask him to hold here, just little bit, do not apply so much force with your finger, ask him to just hold here, you get 2 loops. Ask him to put a 2 finger, another friend, put finger here, you get a 4 loops, right. So, 9 PCR. So, like this will go on. So, load carrying capacity goes on increasing, anyway, that is fine. So, now right now we wanted to work on only n is equal to 1. For n is equal to 1, we call it as mode 1. So, P equal to pi square E I by L square, okay. Pi square E I by L square, okay. Now, you may say, sir, you started somewhere a differential equation, want to solution, and you went somewhere and you are doing something else now, okay. I do not necessary now go back to the differential equation, already I got that. What I needed, I need to get the P, I got it. So, I do not have to worry, go back to substitute there, okay. So, that is my point, okay. So, now once I go there, now what I do, if I try to see this particular P, so at particular point when P I can go on increasing, right. At particular point I will see this column buckles. So, I call it as PCR. That point is again pi square E I by L square. So, I can also say, because I say it is buckled, right. So, this is nothing but my PCR. This is critical load, that is, this is your critical load. At this point column starts buckling, okay. So, very important. So, what is PCR? Critical load. What is I? It is second momentum area, right. Second momentum area, right. That is moment of inertia, right, moment of inertia. And what is E? Is your Young's modulus, right, that we know, right, modulus of velocity, is it not? So, now what we do, that this I is, we have to know that this I is the least moment of inertia, right. Now, I will tell you what is the least moment of inertia. We will tell you what is this least moment of inertia. So, to say that, what I do, I will try to use this I have another equation. Moment of inertia can be also written as A into R square. So, A is nothing but my area of cross section, area of cross section, and r is nothing but my radius of gyration. Radius of gyration, I think you already learnt it. I told you as a part of applied mechanics also, right. Substituting into this PCR, the PCR will become pi square E into I is nothing but A r square by L square, right. Now, if I try to get another form of this, get A this side, right, and R downwards, I can write down PCR by A, right. A I am getting this side, it becomes in the comes in the denominator, pi square E by R square down, it becomes L square by R square. So, I can also write down as pi square E by L by R whole square, right. I hope you understand. Now, look at here, the PCR by A, this is critical load by cross section area of the column, right. This is sigma CR, critical stress, critical stress, very important. The critical stress is nothing but pi square E by, this is L by R, nothing but is my slenderness ratio. Slenderness ratio generally we denote by lambda. So, it is lambda square, very very important, please understand. Now, the point to be noted here, the point to be noted is this critical stress is always less than your sigma y. What is sigma y? Your yield stress. Very important to note this point. It means your buckling is starting much earlier to yielding. Means this equation or PCR is equal to pi square A by lambda square is valid only for the stress less than your yield stress, that means within the elastic limit. When you remove the load, it has to be straight, very very important, okay. Otherwise, this is not valid, okay. So, now very very important, now there is something called slenderness ratio, very important term, slenderness ratio we denote as lambda, it is L by R, the length of the column, right. L is the length of the column, R is the radius of gyration, already told you, right, radius of gyration for the cross section of the column. Now, reason I told you that somewhere in the up that the I is the least moment of inertia, I is the least moment of inertia. What is that meaning, least moment of inertia? That means, if I look at a column with, let us say, if I take a column with something like this, cross section to be something like this, just like a scale, we have a meter scale. So, the scale. So, now when I try to bend, assuming let us say this is my, because any cross section will have a reference axis, right. Let us say this is axis A and another axis is your B. Now, when I apply a P load, I am drawing a plan cross section, okay. So, now if I try to apply a axial load onto this P load at the centroid, it is going to buckle with reference to AA axis only, because AA axis is your weak axis. So, with respect to that axis only, it has got least moment of inertia, right. So, that means if this is your, let us say, width is, let us say T, let us say this is your D, the moment of inertia with respect to AA is nothing but d TQ by 12, and the moment of inertia with respect to the BB axis is your T dq by 12, very high, right. So, now we have to use the least moment of inertia, right, very important, we have to use least moment of inertia, right. This is what I said, PCR is your
critical load.
So, for the critical load I have to use the least moment of inertia, I have to use the least moment of inertia. So, where E is a Young's modulus, right. So, here EI, right, we converted somewhere else up, little up, right. So, EI here, right. Here we are supposed to use the, I told you least moment of inertia, right, here. So, I is least, but now when it comes to this equation, the last equation here, which is again I will write down here, PCR is equal to pi square E by lambda square. Lambda means your L by R. Now, where is my I? There is no moment of inertia now, but moment of inertia is there in the R. R is equal to root over I by A. So, here I is there. Okay. So, use that. That means, right, that means now depends upon the slenderness ratio, my column is, I can say it is critical, column is the I mean that is based upon the slenderness ratio, I will categorize a column to be a long column, there is a intermediate column, or there is a short column. So, depending upon the lambda. So, now, so we know, let us look at this particular equation again here, this particular equation here. What will be my critical lambda, right, at which the column just buckles, still and stable, not buckled at all, right. That means, lambda square is equal to pi square E by PCR. So, just buckle, it is critical means I will say Fy, right, or sigma y, yield stress. So, now substituting pi square in your calculator, okay. Meanwhile, somebody can solve this. E is your material, it is 2 into 10 power of 5 Newton per millimeter square, right. Now, stress is equal to, let us say, 250 Newton per millimeter square. If I can try to find out lambda, that is it means a root. So, what I get, the lambda will be something around 89. I leave to you to find out this. If you do this, you get lambda to be something around 89. That means, 89 is a critical stress, 89 is a critical slenderness ratio, right. Now, 89 will be my critical slenderness ratio. If I somehow find out right, if I try to plot a curve between this lambda here and sigma CR here for a steel only. Let us talk about the steel, for which your sigma y is your 250 MPa, right, Newton per millimeter square. So, what is this formula? Sigma CR is equal to pi square E by lambda square. Very simple, nothing else is there in this. Try to understand, is buckling does not depends upon your material variation, right. It is simply depends upon your slenderness ratio, nothing else, right. So, now if I just go on changing lambda, right, it is a quadratic equation, right. Go on changing lambda, you will see something like this. Go on changing lambda, slenderness ratio. As lambda increases, what happens? Stress, critical stress will reduce. So, something like this will happen. Right, something like this will happen. So, when try to see that something like this. Sorry, I am not able to draw proper curve. Something like this. Okay, this is what we see. That means, if try to draw this particular point here, this is lambda equal to 89. Any value less than means this particular curve. So, lambda it is less than 89, it is strong, I mean short column. Lambda this is less than 89. So, now if you go on increasing here, this is your, I mean you can start from here, intermediate column somewhere, some point, then from there you can call it as a long column. But anyway, my point is only that 89 is your critical lambda, 89 is at critical lambda at which your Euler equation works. So, this is your Euler equation, which is sigma CR is equal to pi square E by lambda square. Very important this one. So, now what happens beyond this? I call it as a straight line. That means, beyond this is not going to go, because not valid here. Beyond this we cannot extend this. Less than the lambda less than 89, this equation not valid. So, I assume to be perfectly straight line, which is equal to sigma y. Assume the yield stress, right. So, now I can continue on. So, there will be a limiting value of lambda with beyond which is not work properly. Let us say something like lambda equal to 100 or 150, if we will say, in the range of let us say 100 to 150, 100 to 150 something range. So, beyond this it will be too long column which will not able to work on, because too much unnecessarily wastage of material. So, we will try to work in this range 89 to 100 roughly. This is the intermediate column. I also call in the long and intermediate, where generally for design of columns, maybe steel column or concrete column. So, this is range we work out. Okay. The slenderness ratio in this range we work out. Okay. So, this is called the Euler critical stress. Euler critical stress is what we see. I hope this is clear to everybody.